Welcome back to Material and Energy Balances. This video will focus on unsteady state mixing problems, which will require the use of coupled unsteady state material balances. The best way to learn about this type of problem is to just do an example problem, I think. So this one says you have a 500-liter vessel that is initially full of salt water at an initial concentration of 2 grams of salt per liter. At time is equal to 0, you turn on a stirrer and begin to flush the vessel by feeding fresh water at a rate of 25 liters per second. And you withdraw saltwater solution at the same rate, which is also 25 liters per second. Obtain a function that describes the concentration of salt in the vessel as a function of time. I'm going to start the solution by doing what I always do in material and energy balances, which is draw a picture of what I have going on. So this is my vessel. I'm going to input the information that I have. I know that it is 500 liters in volume, and I know its initial concentration is 2 grams of salt per liter. So I haven't talked about the notation of concentration yet. I'm just going to call it C for concentration with the sub S. And the word initial here is important. Forgot the I in initial. Initial means that this is an initial condition, right? So looking ahead, I know this is an unsteady state problem. An initial condition is going to be needed to solve the entire differential equation. So this is how I'll write it. CS at time 0 is equal to 2 grams per liter. I have an input stream and I have an output stream. So this is an unsteady state continuous mass balance problem. I do have a problem though, because I'm not given what the mass flow rate is. So I could label this as Mn if I want. But the problem is that we know that the density of freshwater and saltwater is different. So I don't necessarily know what M in and M out are. However, I do know what a V in and V out are. So V out is 25 liters per second, and V in is also equal to 25 liters per second. Okay, what else has the problem given me? At t equals 0, you turn on a stirrer and begin to flush the tank. So stirring, I need to talk about what a stirrer does. This is a very important assumption, the well-mixed assumption. What this means is that there's no spatial variation anywhere within the tank. So you can imagine that if I don't have a mixer, I could have a concentration of salt that is a function of where I am within the tank. But if I have a stirrer that's very good, I can assume that the concentration is the same everywhere. That's the other thing I need to write in my diagram. I need to write what the concentrations of salt are that I have. So in my inlet flow stream, I'm going to call this concentration of salt in, CS in, and I'm going to call this CS. And the reason why I'm going to do that is because the well-mixed assumption allows us to say that the concentration of any outlet stream from a well-mixed vessel is the same as whatever the concentration is inside. So I just pause to write that definition. So I can apply this to the concentration or the composition of a stream that is emerging, which is going to be my outlet stream, is going to be the same as the concentration inside the vessel, which is why I've used the same notation there and there to mean CS, which is the concentration of salt inside the vessel. Now, what is the problem asking me to solve? If I highlight what I'm asked to solve, I want to solve for the concentration of salt inside the vessel. So I want to find CS as a function of T. So this is going to be my main unknown that I want to solve. More specifically, the concentration inside, but I just explained why these are the same number. Now, just like in steady state mass balances, you can start by doing an overall mass balance, or because we have two components within the system, you can balance the salt or the water. I'm going to start with an overall balance, and I'm going to break a rule that I told you last time, which is that you have to always balance a conserved quantity. And I'm going to balance the overall volume first because I see that my volume flow rates are equal. I have that given to me, so therefore I can use that to balance. So step one is to balance overall volume. This is not generally what you want to do, but for this particular problem, I want to obtain an expression for the overall volume. And I'll show you why this is important in a moment. Okay, so even though volume is generally not conserved, again, I'm doing it this way because I have specifically what the volumetric flow rates in and out are. So if I balance V in minus V out and say that is equal to dV dt, so this is an unsteady state balance where I'm not generating nor consuming volume. If I plug in numbers here, I've got 25 grams, 25 liters per second, I'm sorry, minus 25 liters per second, which is equal to 0. So the conclusion of doing this overall volume balance is that dV dt is equal to 0, which means that V is a constant, which you might have been able to look at and see, but it's important to be able to know how to prove these things with math when they get trickier and trickier. Now, armed with the fact that V is a constant, now we can move on to our salt balance. Balance salt. And you'll see why I wanted to balance volume here when I do my salt balance. So for balancing a chemical component, I want to start with a quantity that is conserved always. So I'm going to balance the mass of salt. So I'm going to say the mass flow rate of salt in minus the mass flow rate of salt out is equal to the change of mass of salt with respect to time. And now, in order to get this into something meaningful, I mentioned that we don't know what M in and M out are because we don't know what the density is. We know that the density is changing, but I don't necessarily have a table of the density of salt water as a function of concentration. However, I can express mass in a different way. Express mass in terms of a quantity of interest. And my quantity of interest for this problem is the concentration, right? That's what the problem is asking me to solve for. And the concentration is in units of a volume per time. Right, so if I know that and I want to express mass in the flow rate, if I multiply the volumetric flow rate by a density is the one that we've been doing, but I can also multiply it by the concentration in order to get mass. So this is, again, just by doing a unit analysis, I know that mass is equal to concentration times volume by looking at the units, right? Mass is going to be in grams. Concentration was given to me in grams per liter, and volume is liter. You could say the same thing for volumetric flow rate. So mass flow rate is grams per time. Volumetric flow rate is liters per time, and the same expression would be true. So I'm now going to replace in my mass balance on salt these terms with the terms of concentration and volume. So the mass of salt in, I'm going to rewrite to say that it is the concentration of salt in the inlet stream times the volume. Sorry, that C should not have a dot. The volumetric flow rate is a flow rate, so that one needs a dot. So concentration of salt, again, times the volumetric flow rate is going to give me the mass of salt in minus the mass of salt out. So C sub S times V dot out is equal to D CS times V dt. So it's important to differentiate. Students get confused about this all the time. So this V up here is the volume of the tank. In contrast, these V dots are volumetric flow rates in and out. Right, so in terms of what the problem statement told me in terms of parameters, V in and V out are 25 liters per second. This V is the volume of the tank, which is 500 liters. So I need to make sure I keep that organized in my head. All right, what's next? This is now a differential equation that I can solve, and I can start plugging things in. So concentration of salt in is equal to 0 because I have pure water coming in. and therefore it doesn't have any salt in it. So that is going to kill the entire first term. I'm going to keep the second term as minus CS times V out. And on my accumulation term, I've already proven that volume of the tank is a constant. So volume up here was referring to the volume of water in the tank. I guess that's important, right? It's not the volume of the tank itself. This is the volume of water, of salt water in the tank, to be more specific, right? So because that is constant, I can pull that out of the derivative and call it V times, oops, V times dCs dt. And voila, I have a differential equation that I can solve. I'm going to refrain from plugging in any numbers until the very end, because that's good engineering practice. All right, I have a separable differential equation here. I know that neither V out nor V is a function of time, but CS is a function of time. So I'm going to separate my variables. And because V and V dot out are constants, it really doesn't matter which side they go on. So because it doesn't make much difference, I'll just put them on the left-hand side. So CS times V out over V dt is equal to dCS. And I'm going to integrate both of those. Oh, wait a minute. Didn't separate variables properly. I need to take the CS over to the other side. So I'm going to keep V dot out over V on this side. dt equals dCS over CS. That's looking better. Okay, integral of the left-hand side is minus V out over V times T. Integral of the right-hand side is ln of CS. Can't forget about the plus C. I'm going to put that in on my independent variable side. Now my next step is I have to solve for CS as a function of time. So CS of t is equal to, exponentiating both sides is going to give me C e to the minus V out over V times T. And then I can plug in my initial condition to solve for C. So my initial condition, if I scroll up just to check, was that CS at time 0 is equal to 2 grams per liter. So if I plug in 0 here, I'm going to obtain 2. So 2 is equal to C, exponent of 0, which is canceling to 1, and that gives me that C is equal to 2. So answering the question, CS as a function of time is equal to 2 times the exponent of minus V out over V. Well, so I guess I can plug in values here because I already plugged in the 2. All right, V out was 25 liters per second. The volume of the tank, I think, was 500 liters times T. So this is the answer to what the problem asked me to solve for. Very important that you keep double checking yourself. So double check your units always. So if I say this another way, I meant to write the initial condition in another way. You can call this CS naught. Or, well, I'm not going to, that would be confusing, I think. Just double checking my units. This has units of grams per liter because this is my initial condition. Liters per second over liters is 1 over seconds. And if time is in seconds as well, that means the entire argument of the exponential is going to be dimensionless, which is what I want. And my units are going to cancel to give me grams per liter. So that's what I mean by double checking your units. What you can also do is double check your initial condition. So again, if I plug in a 0 here, then this whole term is going to go away because the exponent of 0 is going to be 1 and my initial condition of 2 is going to be true. Another thing that you can do to check yourself is to plot this. So I know that exponential decay is going to start at 2 and kind of decrease like that. So that this graph kind of makes sense with what you would expect. Okay, so now let's try the same problem again, but let's complicate it a little bit by making it so that the outlet volumetric flow rate is not the same as the inlet. So let's redo the problem now. Okay, so what changes about this problem? Perhaps obviously my volume is not going to be a constant as a function of time now because my volumetric flow rates in and out are different. So I'm very slowly going to be draining this tank overall because I'm letting out more saltwater solution than I'm putting in fresh water. So once again, I'm going to start with a volume balance and say that V in minus V out is equal to dV dt, which is the only, again, I want to stress the fact that the only reason why I'm balancing volume here is because I know what exactly the volumetric flow rates in and out were because the problem gave them to me. Normally, balancing volume is a very bad practice, and I would not recommend that you do that unless you have this exact situation where you're given what the volumetric flow rates are. So plugging in numbers again, 25 liters per second minus 26 liters per second is going to give me dV dt. And quite obviously, dV dt is equal to minus 1 liter per second. Now you can solve this differential equation to obtain a function for v of t. Right, so if I bring dt over to the other side, I'm going to get v is equal to minus t plus c. More properly, v of t is equal to minus t plus c. And by plugging in my initial condition, I know that v of time 0 is equal to 500 liters. So therefore, this is also going to be equal to my c. So putting these all together, v of t is equal to 500 liters, 500 minus t. I had to stop myself and just double check my units, right? Because I want to stress that double checking yourself is always good, right? 500 has a unit of liters, and you may say, well, time has a unit of seconds, so you can't subtract liters from seconds. The reason why I initially got confused is because I should have initially put 1 times t, where this unit of 1 has a unit of liters per second, because that is my rate of my net drainage, if you will. And I just didn't write the minus 1 because we typically don't write coefficients of 1. But just as an explanation of that's where my units are coming from, and that's why my units are working out in this case, or how I can just say that volume is 500 minus t. All right, so that is going to enable me now, because I know that volume is not a constant. Now I can go solve the salt material balance. And that's going to have the same procedure as what I just did, although it's going to become slightly more complicated. So M of salt in. Okay, substitute the terms. The mass of salt in is the volumetric flow rate in times the concentration of salt in, which is 0. So that negates the whole term, minus V out times CS of T is equal to, now DMS, remember, is dCS of T times V, except volume is, remember, not constant. So dV dt over dt. And now it's complicated because I can't pull this V out of the differential term. So I have to expand this with the product rule. So I have to say minus V out times CS of T is equal to V of T times dCS of T dt. It helps me sometimes to keep writing these parentheses to remind myself what is a function of time and what is not. So that's why I'm doing this. Remember again that this does not mean that I'm multiplying by time. It just means that whatever variable I have is a function of time. So again, don't be confused and think of that I'm multiplying by time here. Plus CS of T times dV dt. All right, and now this is what I mean when I say coupled differential equations, because I have two differential terms. But I already know what dV dt is, right? Because I solved for it above up here. Right, I already know that dV dt is minus 1 liter per second. Okay, so that helps a little bit. I also know what V of t is, so I can plug that in as well. So minus V out CS of t is equal to V of t is 500 minus 1t plus forgot dCs of t dt plus CS of t times minus 1. And I've actually not checked to see if this is separable. I guess we'll do that now. So let's try and consolidate and separate variables. So I'm just going to do some algebra here. I think this is going to work out. So this is after one line of algebra. I've just brought this CS times minus 1 over to the other side and factored out a CS of t. If I want to separate these variables now, I can say that bring 500 minus t over to the left-hand side, bring the dt over to the left-hand side, and then bring everything over to the right-hand side. 1 over 1 minus V out. I kept the units up here so that you could see what I was doing, right? I always want to make sure that my units are consistent. 1 minus V out times CS of t. Actually, that is a constant, right? So I can actually factor that out of my integral. So I'm going to write that as 1 over 1 minus V out times 1 over CS dCs. Okay, and then I integrate. Integrating left-hand side is going to give me minus ln of 500 minus t. Integrating the right-hand side is going to give me 1 over 1 minus V out times ln of CS. Forgot about the plus c again on my independent variable side. And now I can solve for t. Sorry, solve for CS. That's what I want to solve for. I want to solve for CS. I had to make sure that I did my math right. I think this is correct. I did my steps correctly. I can now plug in my initial condition, which is that time equals 0. My initial concentration is 2. So 2 is equal to C times 500 to the V out minus 1. I suppose I could put in my number for V out. V out, remember, was 26 liters per second. So 26 minus 1 is 25. And C is therefore 500 to the 25. And now if I plot CS of t, this is my final expression, by the way. Wait, nope, I didn't do that right. It's 2 divided by 500 to the 25. So CS of t is 2 over 500 to the 25 times 500 minus t to the 25. I could do some algebraic cleaning up of this equation, but this would be the final answer. So I encourage you to go into Excel and to plot CS of t with this problem versus CS of t with the first problem. Even though they look different, it's very interesting to me that they actually give you pretty close to the same thing. So a difference of 1 liter per second for a 500 liter vessel is actually not that significant. And then you can play around with this too. Play around with the parameters. So try a different size vessel. Instead of 500 liters, try 400 liters and see how that changes the shapes of your profiles. That'll be all for this video. Thanks for watching.